They're asking us to seal the ductwork. And this is an example of a mastic sealant. It's applied with a brush, comes in a can, very thick. It dries and cures to a hard condition, not unlike cement. It's a very good sealant. You can seal the ductwork, however, in a number of methods, including tape. But not all tapes are suitable. The cloth duct tape that you will purchase at the hardware store, you have found out if you leave it in place on anything a long period of time, the adhesive will cure and the tape will fall away. Well, there are aluminum foil tapes on the market as well. And some of them even have little fiberglass reinforcing threads in them. And they work very well. Ductboard, fiberglass ductboard has an aluminum foil vapor barrier, and there's a tape that goes over the joints and seams on ductboard that's permanent, lasts for the life of the building. But not all tapes are that way. At a science building that the university built a number of years ago, they had very large rectangular ductwork in the big mechanical rooms, and it was insulated with a rigid fiberglass board with an aluminum foil vapor barrier over the outside of it. And the contractor covered all the joints and seams with an aluminum foil tape that had the fiberglass reinforcing threads in it. And it looked beautiful, gorgeous. But the university has a warranty period on all their new buildings. The contractor's to come back at the end of 1 year and fix anything that's gone wrong. When he came back, all that tape was lying on the floor. It didn't even last 1 year. So a tape that you would think would be an expensive aluminum foil commercial tape might not even be suitable. My preference is for the mastic brush-on duct sealer. It may not look very pretty, but it works very well. All ductwork has to be sealed, and ductwork with internal air pressure of 3 inches or greater must be pressure tested. In order for the contractor to know which ductwork this is, it must be identified on the drawings. The maximum permissible air leakage is specified in this section. Now, here's something for you architects and engineers that you must build into your cost, your proposals, your fees, because you are now required to do more things. You must automatically complete as-built drawings. That's part of your fees. You have to do that. You must prepare operating and maintenance manuals. Now that obviously means you're going to gather all the operation manuals from the products that you selected and were installed. So the contractor is going to have to gather them from the equipment as it comes in and save them. But you're going to need more than one, and I suggest that you have 3 copies of the operation and maintenance manual. And the 3 copies are prepared not only with the data from the manufacturer, but you're going to have to write, or the engineer will, the intentions of how the systems were to be operated. What the set points are, what the operating schedules are, what the flow rates are, how the pump is intended, how the heating and cooling systems are intended, all of these things. And this then you will submit to the owner. And as I mentioned, 3 copies I suggest, because if you give them only 1 copy, most private owners don't know what to do with it. They will lose it immediately. So I would suggest that 1 copy be retained by the engineer, 1 copy given to the owner, and 1 copy given to the maintenance company. Now it may be in-house maintenance for a large owner, or it may be contracted maintenance. And that should stay with whichever maintenance company gets the contract. System balancing must be performed. Air balancing, water balancing. System commissioning must be performed. This is operating all of the systems to make sure that they work just like the owner wants them to and the engineer designed them to. I have found pumps running backwards. I have found systems misconnected where piping's been reversed, controls reversed, valves installed backwards. All sorts of things that only an actual operating test would find. So that's what's called system commissioning, and this is now required by the Energy Code, part of the family of building codes. So this has to be built into the original budget. Now the prescriptive requirements we've just outlined. There are mandatory provisions, and then we can do prescriptive, we can do energy cost budget, we can do the simplified approach for small systems, which lead us into demonstrating compliance with the code. The prescriptive path we outline here, all the different features of the prescriptive path. Economizers. Economizers are a system of dampers. Let's talk about air side economizers. A system of dampers, ductwork, and outside louvers that bring outside air in to cool the building when the conditions are just right outside. And you can shut down the mechanical cooling equipment. And an air side economizer provides outside ventilation air 100% of the design supply air. Now, over the years, as a rule of thumb, engineers have come to utilize 55-degree supply air temperature to maintain a 75-degree air space temperature in the cooling season. Just a rule of thumb. You can put colder air in, less volumes, but it takes less air. You have to worry about cold drafts and things like that. But over the many decades, 55-degree air yields a 75-degree environment. So if it's 55 degrees outside, why not bring in full outside air, shut off the chillers and the condensers, and cool the building with that air? That's what's called an economizer. Well, why not use outside air as much as possible? Let's say it's 65 degrees outside air. You'd need to run the chiller a little bit, the air conditioning equipment a little bit, to cool it down to 55. But it's cheaper than cooling the 75-degree return air down to 55. So at 70 degrees outside, it's still cheaper to cool the 70-degree air than it is 75 return air. At 74 outside, it's still cheaper to cool 74-degree air than it is 75-degree air. At 75 degrees outside, it's the same temperature, no difference. The only consideration is, would you rather have return air or would you rather have fresh air in your building? So between 55 and 75, you want to go to full outside air. That's what the economizer does. Below 55, you return to the minimum settings required for ventilation in the building as set by the ASHRAE Standard 62. And above 75, you return to the minimum settings as well. There's only one exception to that, and that's humidity. If it's too humid outside, if it's raining, if it's in a humid summer climate, it may cost more to dehumidify the outside air, even though it's cooler, than it would be to cool the dry inside air. And that's called enthalpy. Enthalpy means the sum total of the heat content of the air, the sensible heat and the latent heat. The sensible heat as measured by a dry bulb thermometer, and the latent heat, which is calculated by measurements from a wet bulb thermometer. That's called enthalpy. And so enthalpy controls are required. Use the outside air whenever possible, but if the enthalpy controls say, nope, it's too humid, it's raining outside, costs too much to dehumidify that, then we don't use it. There are some exceptions to using economizers. I'm not going to go through all these exceptions. They're enumerated in the code. Economizers in all three of our Michigan climate zones are required for HVAC systems with a cooling capacity of 135,000 BTUs per hour or larger. Economizer control signals, they have to be sequenced to the mechanical cooling system and not by only mixed air temperature. You might have a temperature sensor in the return air and another in the mixed air of your HVAC system. And that does not give an accurate representation of when to operate the economizers. They don't use that. And if it's too hot outside, shut off the economizer. Go to recirc. The dampers, again, we say for the third time, have to meet the minimum leakage standards. And when you're going to pull in all this outside air for cooling, you have to get rid of it. Now, there are two means of getting rid of it. One is a relief damper, which is gravity, simply relies on the pressure inside the building. Another is an exhaust fan, which has the capability of moving the exact same amount of air that you're pulling in the fresh air dampers. So you have to be concerned about overpressurizing the building if you're talking about using economizers. Now there's such things as water economizers as well. If your building is cooled by chilled water, there's a machine down the basement that's making this stuff. And it takes the heat from your building and throws it away outdoors through some kind of a heat rejection device on the roof. That can be a cooling tower, or it can be an evaporative condenser. Now, if it's cool enough outside, they're saying, why not use the cold air directly to make chilled water rather than having to run this machine? So they're saying, if the air temperature outside is cool enough, use it to make cold water. Well, remember the 55-degree air temperature. Typically there are 10-degree differences between fluids in a heat transfer situation. So to make 55 degrees, you need 45-degree chilled water. And if you have air outside and you need 45-degree chilled water, that air has got to be about 35 degrees. So if it's cool enough outside and you still have a cooling load in the building, which might be a process of some kind or interior spaces, computer rooms, anything, it could be in a commercial building, use a water side economizer. Now the water in the condenser going up to the cooling towers is dirty. You don't want it in the clean water which is circulating through your cooling system. So what you do is you put in a heat exchanger, and we shut off the chiller right here, close that valve, shut off that pump, and we now run the cooling tower water through this heat exchanger. And the dirty water stays in this loop, and the heat exchanger transfers the heat to the clean water circulating in the chilled water loop. The economizer controls have to be integrated in the whole control scheme. They have to make sure that the proper pumps shut off, the proper valves close, and everything operates in unison when we want to run this. We also have to make sure that whatever we're doing does not increase the energy used to heat the building. Whatever we're doing to help in the economizer cannot affect the heating system in an adverse way. Zone controls are specifically detailed here. Zone controls, as we went over before and discussed, must prevent reheating of heated air. We want to heat it once. Recooling of cooled air. Mixing hot and cold air. There used to be HVAC systems called multi-zone systems, where you would heat a hot water coil or a steam coil, cool a chilled water or direct expansion coil, have them both hot and cold at the same time, and dampers directing air over both coils. And then you'd have a hot air stream and a cold air stream that would be mixed by the dampers to the exact requirements of that particular room over there. That is no longer allowed. You cannot do the simultaneous heating and cooling. There are some exceptions to the zone control systems. I'm not going to go through all these exceptions. They're printed for your reference in the book. Hydronic system controls. Hydronic means heating by means of water or cooling by means of water. Chilled water cooling, hot water heating. Three-pipe systems are no longer approved. Hydronic systems would frequently have a water chiller and a boiler in the mechanical rooms that for economic reasons use the same set of piping. And they could either have two pipes, one supply and one return piping going out to the building, or three pipes, a hot water supply, a chilled water supply, and a common return coming back, which could go either direction, or four pipes, supply and return from the boiler, supply and return from the chiller going out to the apparatus. Three-pipe systems cause such problems that they have been outlawed. They do not want accidental chilled water coming back going into a boiler. The cold water coming into a hot boiler will crack it. It will physically break the boiler. Likewise, hot water going into a chiller can cause some severe head pressure control problems in a chiller. Now, two-pipe systems, where you use the same set of pipes for either hot water or chilled water, are approved, and they are an economical way of doing it. But you must put controls in to prevent the simultaneous operation and to make sure there is, in effect, a deadband or a time-out period between when one machine operates and the other one is required, between when the boiler is required to operate and when the chiller is required to operate. For instance, a building may be cooled by nighttime temperatures. In a dry climate, it can get very cold in summer nights. In fact, you can have below freezing temperatures in the desert during a summer night. So you may need heat in the building at night. But then the sun comes up and suddenly the day warms up and you're going to need air conditioning. So you may have to run the boiler at night to heat the place and run the air conditioning in the daytime to cool it. So they're saying if you have a situation like that, you have to have at least 4 hours between when the boiler shuts off and when the chiller starts. And again, at the end of the chiller operation, at least 4 hours between when the chiller shuts off and when the boiler starts. And that's to let the water temperatures equalize naturally in the piping. Now, there's a system called a heat pump system in a water loop. And what this means is that inside of a building, there are pipes circulating water. And the interior spaces in a building may require cooling all the time. There may be enough heat-producing activities going on where you're going to have to air condition them night and day, summer and winter. But yet the outside surfaces of the building and the outside spaces will need heat in the wintertime and, of course, cooling in the summer. So in the wintertime, why not take the heat from the inside spaces and transfer it to the outside spaces? Heat the building with your waste heat. And that's what a water loop heat pump system does. There's a circulating piping system with water, and little heat pumps, which are basically refrigeration machines, will cool the air in the inside space and dump the heat into the water through a refrigeration compressing mechanism into the circulating water loop. Where on the outside spaces, another set of these little heat pumps, one for each space, will take this warm water and extract the heat from it and through another refrigeration process reject it into the space. So we can transfer heat and cool between spaces by means of a heat pump water loop system. They say in the energy code that there has to be a deadband of at least 20 degrees between the heating cycle and the cooling cycle of these heat pumps. Again, to prevent short cycling and to prevent overlap of operation. And in the summertime, when all this heat has to be rejected and we need to air condition the building, we have to throw it away. Everything has to be thrown away through a cooling tower. So we have to have valves and dampers to isolate the cooling tower when it's not needed in the heating system and we want to capture all that heat. Dehumidification. Again, we must prevent humidification and dehumidification from simultaneously occurring. We used to cool to dehumidify and then reheat to bring the air up to the comfort level in the space. That is no longer allowed. However, there are some exceptions to that. Basically, small systems you don't need to worry about. Systems that are 6 2/3 tons, they can unload down to be small systems you don't need to worry about. And process applications in industrial environments we don't need to worry about. Now again, here's the water source economizer as we talked about that. Systems with hydronic, cooling, and humidification systems shall be designed to maintain an inside humidity greater than 35-degree dew point. They shall use a water side economizer if an economizer is required, and we've described the operation of the water economizer already. Fan horsepower. For motors larger than 5 horsepower, we have to worry about how much energy they use. There's a limit and there's a formula in the code for calculating this maximum horsepower. For part load, for static pressure sensors on variable air volume systems, and for set point resets. There's a whole table and a whole formula for static pressure reset and for fan power limitation. We figure that most of the time a heating and air conditioning system runs at only a fraction of its full capacity. The full capacity is sized for the maximum heating environment in the wintertime, the coldest winter temperatures, or the maximum cooling environment, the warmest outdoor temperatures in the summertime. And for Michigan, in the central Michigan area, we're looking at about 3 degrees above zero is our design winter temperature, and 91 degrees, as if my memory serves me, for our design summer temperature. Well, most of the time we don't reach those temperatures. We're operating in the 80s in the summertime and in the 20s in the wintertime. So the systems are never operating at their full load capacity. So what they're saying is that for fans larger than 5 horsepower, the selected fan motor shall be no larger than the first available motor size, greater than the brake horsepower. And there are a couple of exceptions. The fan power required to move a given volume of air is limited by a formula. And there are requirements specific to variable air volume fan systems. Special systems such as variable air volume systems have special considerations for their fans. Fans larger than 10 horsepower have to have variable speed drives or must be a vane axial fan with variable pitch blades. There used to be a scheme also of radial inlet dampers on a centrifugal fan. And basically they want to reduce the air flow instead of pressurizing the ductwork. And at the time, you reduce the horsepower on the fan. And they say that they want controls to reduce the horsepower so that when the airflow falls to 50% of its design volume, we want to reduce the horsepower down to 30% of the maximum horsepower. And the location of the pressure sensor in a variable air volume system is critical. And believe it or not, the energy code specifies where you'll put the pressure sensor. And they say, place the sensor in a point in the ductwork so that it's going to be sensing the 1/3 point of the total design fan static pressure. Well, you can calculate where that is because you know what the pressure drop of the ductwork is at maximum airflow. So if your fan has a discharge static pressure of 3 inches and you need 1 inch to operate the boxes at the far end of a 200-foot long duct, you can figure that you've got a 2-inch drop in pressure at that point, and there's, say, 1/3 of the way out, so 1/3 of 2 inches out in the system where you calculate that pressure would be is where you place the sensor. That's in the energy code, believe it or not. Set point reset. They want the set point of the air temperature to be reset according to room demand. And the pressure must be set in a variable air volume system. Reduce the pressure according to demand. If demand drops, if there's nobody in the room, nobody in the building, few occupants, they want the air pressure to drop so the fan horsepower can drop. And we don't waste energy operating the system needlessly. Again, hydronic systems are heating and cooling with water. And so hydronic systems with a pump horsepower larger than 10 horsepower have to meet a whole bunch of requirements. And basically the concept is that they want to reset the temperature to lower temperatures for hot water or higher temperatures for chilled water when the demand is less. They want to isolate the pumps. If you have parallel chillers or parallel boilers and you're shutting off several at low flows, shut off the pumps as well so you don't circulate water needlessly through an idle boiler or chiller. Parallel systems, you want to isolate the pumps so they don't flow backwards through an idle pump. Boilers typically have temperature reset according to outdoor air temperature. So hot water heating boilers, the temperature normally gets reset. For hydronic heating or cooling systems that have temperature control valves on terminal units that modulate open and closed, the circulating pumps shall vary their flow rate according to a differential pressure sensor. And for big pumps, over 50 horsepower and working against pressures greater than 100 feet of head, the requirement is to reduce the power input to no more than 30% of full load at 50% water flow. There are some exceptions, however. The pumps have to be isolated in large chilled water plants, for instance, which are common in campus district heating and cooling systems. You might have multiple chillers. You might have pumps on them 50 horsepower, 75 horsepower or more. And when a chiller is idle, shut its pump off. Close the valves to make sure that the water from the other pumps does not circulate through the idle chiller or the other pump. Temperature reset controls. Systems with a design capacity of greater than 300,000 BTUs shall reset the temperature of the hot water or the chilled water supply. Again, boilers, this is typically done automatically. Colder the temperature outside, the hotter the water. As the temperature outdoors warms up, To prevent over control, we reduce the water temperature. It's done automatically. Hydronic heat pumps. Remember all these little heat pumps I was telling you about to transfer heat from the interior building spaces of a building to the exterior? They're saying when a heat pump shuts off, have a valve on that heat pump that shuts water off to the heat pump, so there's no flow through the idle heat pump. As more and more of these heat pumps shut off, as more and more of their valves shut off, the central circulating water system flow requirements are less. So then the pump would slowly reduce its water flow. It becomes a variable flow system. The heat rejection equipment on the roof, which is cooling towers, air-cooled condensers, evaporative condensers, they say have variable speed controls on them if they're larger than 7.5 horsepower. It used to be you'd have a 50 or 100 horsepower motor on a cooling tower on the roof, and you could hear it several blocks away, starting up and shutting down. And it's a very annoying thing. But if you have a light load in your building, air conditioning requirement is very little, and you have a large cooling tower, why not run the fan speed at a slower speed? So they said instead of having start-stop controls or even two-speed motors on these cooling towers, have variable speed drives on them. In other words, don't waste motor horsepower needlessly. And they also want us to recover heat from exhaust air through either HRVs or ERVs. HRVs are heat recovery ventilators. ERVs are energy recovery ventilators. They recover about 3/4 of the heat from exhaust air. And they say in large systems greater than 5,000 CFM, they want at least half, 50% energy recovery. Exhaust air, which is typical in research buildings, laboratory buildings, anytime you have processes exhausting heat or fumes, here's a whole bunch of regulations for those. Basically, however, there's some exceptions, and commercial kitchen hoods, we don't want to have an energy recovery ventilator in a kitchen hood. Toxic fumes, flammable, paint or corrosive fumes, we don't want an energy recovery ventilator. Climate zones 1 through 3 heating systems, we don't need energy recovery ventilators. Cooling systems in the northern climate zones don't need them as well. Service water heating. If you have large hot water heating systems for domestic water in buildings, large office buildings, maybe large high-rise residential buildings, they say let's use some heat recovery. Let's use waste heat from chillers to heat domestic water. Let's try to utilize the waste heat instead of throwing it away. And again, there's some exceptions. Kitchen hoods, we have a requirement of makeup air for kitchen hoods which are sized 5,000 CFM or greater, but the Michigan Mechanical Code supersedes this portion in the Energy Code. The Michigan Mechanical Code says that makeup air is required for all commercial kitchen hoods regardless of the size. Fume hood exhaust have to have heat recovery for makeup air. Direct makeup air, where you don't heat or cool it, direct right to the hood, and that's done in many research buildings on the MSU campus. Or we have to be able to shut the hood down to minimum airflow if you lower the sash on the fume hood inside. So you have a variable airflow according to the sash position. Radiant heating systems, which can be a hot water in the floor piping system, or it can be an electric or gas-fired overhead radiant system. They say they are required for unenclosed spaces except for loading docks with air curtains. What would an unenclosed space be? I've thought long and hard about that, and about the only thing I could think of would be a gazebo or a band shell. Would be an unenclosed space, because every other space would be enclosed, and a loading dock, of course, would have the big doors open periodically. But anyway, they say they shall be installed in conformance with governing provisions of the standard. But nowhere can I find out what standard means. So that's an interesting little query that we might have to address in one of the future code editions. Hot gas bypass in refrigeration systems is a means of controlling the capacity of a refrigeration system or air conditioning. You might have a 10-ton air conditioning system, but for a period of time you might have only 3 tons of load in a space. And so to make a 10-ton air conditioning system serve a 3-ton load, you'd have to start it and stop it, and then start it and stop it, and then start it and stop it. So instead of doing that, there's a concept called hot gas bypass where you could put an artificial load on that compressor. So you could take the hot gas coming out of the compressor and put it right back to the inside and put an artificial load on it and make the compressor thinks that it has a 10-ton load. It will therefore operate continuously. And the inside room controls of the air-conditioned space will then vary the hot gas bypass in accordance with the needs of the space. More people come in, there's less hot gas bypass. Less people, more hot gas bypass. That is wasteful. And what they're saying is try to select a compressor with multiple steps of unloading or continuous capacity modulation. We now have variable speed compressors where the compressor speed varies exactly with the load. No horsepower wasted, no cycling. The compressor does not need to start and stop, which will eventually destroy the system. So select compressors with continuous capacity modulation, which means variable speed. And there is an exception, less than 90,000 BTUs, which is about 7.5 tons. Again, the submittals that are required, record drawings, operation maintenance manuals, balancing commissioning, we already talked about these things. Talked about the record drawings. All of this information that's required to be provided by the engineer costs money. Somebody's going to have to build this into their initial proposals and make the owners aware that your proposal for design of this project includes all of the things that are now required by the new energy code. Okay, systems have to be balanced in a written report for any spaces over 5,000 square feet. Here's how to balance the system. They even tell you that you have to do a proportional balance and that you should trim the pump impellers or again install variable speed systems to make sure the pumps don't waste energy. Systems less than 10 horsepower pumps are exempted. Have to commission the system, making sure it operates like the owner wants it to operate. And of course, we have to comply with all of the efficiency tables that are published in the code. So now, for domestic water, we also have mandatory provisions. And we can also use 3 methods of demonstrating compliance: the prescriptive, the trade-off, or the energy cost budget method. For surface water heating, the mandatory requirements are load calculations. We have to size the equipment properly for the demand, whether it's an apartment house, a process machine of some kind, manufacturing, restaurant, whatever. We have to demonstrate we've sized it properly. There are mandatory efficiency requirements for the heating apparatus. We have to insulate the piping. We have to have controls on it. And it also addresses swimming pools. That's part of service water heating. We have to provide load calculations. We have a table of efficiencies for hot water heaters. We have to insulate the tanks. The piping has to be insulated. Circulating piping has to be insulated. There's some exemption for the first 8 feet of piping around a non-recirculating system. We have to have controls. For instance, here's a recirculating pump. You see the piping is insulated, but basically when there's no demand, when people are asleep at night or when the offices are closed, shut off the pump. Let's not recirculate the hot water needlessly. We have temperature maintenance controls. In an alternative to a pump, we might install a heat tape on the hot water supply piping under the insulation. We eliminate the need for the return piping in the pump. Well, you shut off the heat tape at night when it's not necessary. The temperature controls have to allow for the storage temperature adjustment from 120 degrees down to a maximum temperature compatible with the intended use. For Michigan, under the barrier-free codes, we're looking at 110-degree water supplied to fixtures. So we have to be able to adjust the water temperature down. Exception, if the manufacturer's instructions specify a higher minimum thermostat setting to minimize condensation and corrosion in a non-condensing heater. In a standard water heater, you cannot set the temperature too low. If the temperature in the tank is too low, the gas flame playing on the tank, moisture will condense out of the gas flame. And the moisture on the outside of the tank will corrode it. And over a period of time, it'll rust right through. So you cannot set the temperature too low in some design water heaters, which means you might be setting the temperature at 140 degrees and then relying on mixing valves at the point of use to keep the temperature down to the barrier-free requirements. Shut the systems off when they're not needed. Again, we might have to mix hot water down to a temperature for the barrier-free requirements. Circulating pump controls, they want to shut off the circulating pump from the start of the heating cycle to a maximum of 5 minutes after the end of the heating cycle. Well, what they're talking about is not the pump taking water to the extremities of the building, but the tank that stores water from a boiler. Because in a mechanical room, you could have a storage tank water heater, or you can have a boiler which has no storage tank attached to it. And sitting beside it will be a tank of several hundred gallons capacity and a circulating pump going between them. So what the intent of this portion of the code is that's the pump between the boiler and the storage tank, not the pump between the storage tank and going out to the extremities of the building. That operates continuously, shut off only at night. This pump between the boiler and the storage tank operates only during the heating cycle. And what they're trying to do is to minimize the stack losses, having hot water go through an idle boiler and having natural draft take the heat and cool that water and throw the heat up the chimney. Swimming pools. Got to be able to shut the pool heaters off, so the switch has to be accessible to users of the pool. So if you're not going to use it, there's nobody there, the last person shuts it off. They don't want a standing pilot light for gas-fired pool heaters. You have to have a pool, it says vapor retardant pool covers. Well, that would be an insulating cover as well as vapor retardant. The exception is unless most of the heat comes from solar heating or some kind of non-fired heat, does not use any kind of fossil fuels. Time switch is required. Again, shut it off at night. Shut the whole system down when it's not necessary. For domestic hot water heaters that don't have a circulating pump on small systems, they say they want heat traps, which are loops of pipe that prevent thermal siphoning of the hot water up through the system. If you have a system that provides both space heating and domestic water heating simultaneously, it has some requirements, special considerations for a combination system. For electric power, the code basically covers voltage drop. And it's different from the National Electrical Code. The NEC covers the voltage drop in feeders, large electrical cables, and branch wiring. The Energy Code also covers the voltage drop in feeders and branch wiring, but it's more stringent. It says thou shalt have less voltage drop than the electrical code. For electric power systems, again, record drawings, as-built drawings are required. It says within 30 days of the completion of the project. Isn't that interesting, having that in the Energy Code to tell the architect or the engineer that within 30 days he has to complete his as-built drawings? That's a little caveat many people never thought about. And of course, there have to be operating and maintenance manuals for the equipment. Now we get into the lighting system. And again, there's prescriptive and trade-off and energy cost budget methods for complying with the lighting requirements. There's compliance paths. There are some mandatory provisions that must be met regardless of which compliance method you choose. But there's two methods for interior lighting power allowance. One is the total building area method and one is the space by space method. Those are some alternatives allowed for you. The lighting systems basically cover every place a human can occupy. The exterior, from where a person might park a car in a parking lot and walk at night up to a building entrance, and then inside, the corridors, the office spaces, the utility spaces, the bathrooms, all these different spaces have different requirements, and they're all enumerated in the lighting code. The exceptions to the code are emergency lighting, which are the little wall packs that you see that come on when a power fails, exit lighting, within dwelling units of a building. So the code, if you have an apartment building, within the dwelling units in the apartment building, the lighting requirements do not have to comply. Life safety lighting, for instance, exit lights are not covered, or decorative gas lighting. Gas is not electricity, obviously. So new lighting and lighting controls must comply with this section unless an alteration replaces less than half of the luminaires in a space, and that alteration does not increase the installed lighting power. So if we were going to replace less than half the light fixtures in this room, we don't have to worry about it if we're not increasing the power. We don't want to go to less efficient fixtures. They use a term called lighting power, and this is the wattage of the lamps. They're not talking about the lamps themselves. They're not talking about the fixtures. They're not talking about lighting levels. What they say is the lamps used to light a space can have no more than so many watts. A particular space can be addressed by itself, or an entire building can be addressed if the spaces are similar. There's mandatory requirements of controls, switching, and lighting efficiency. There are interior lighting power limits, again, the wattage used to light a space. And then there are exterior lighting power limits, and we're going to talk about all these different things. We have a whole building method or the space by space method for calculating interior lighting power limits. We have some tradable and we have some non-tradable areas for exterior lighting. Luminaire wattage. The wattage of an incandescent lamp, because it's a pure resistance element, is what's printed on the lamp. However, the wattage of a fluorescent light that has a ballast, or a transformer as it's known, there's some losses in the transformer that add to the wattage that's printed on the lamp. And the older ballasts, the older transformers, were actually iron core transformers, and they had losses in them that were 20% of the wattage printed on the lamp. So for instance, a 40-watt fluorescent tube, the tube drew 40 watts, the ballast drew an additional 20% of 40, or 8 watts. So if you use a fixture that has a ballast, you have to calculate the additional losses of that ballast. Now, I will say that technology has progressed, and we are now using, to the greatest extent, electronic ballasts, and these don't have any losses. So you could take the luminaire wattage printed right on the lamp and use that in a calculation. For a track light, you could put lots of little fixtures and clip them onto a track light. So the code says that for a track light, you must calculate a minimum of 30 watts per foot, or the wattage limit of the system circuit breaker. So if you have a track light on a 15 amp circuit, you have to calculate that that circuit breaker, 15 amps, would be fully loaded by fixtures that you put on that track light. For low voltage lighting, you calculate the transformer wattage. I have low voltage lighting in my home on a dimmer, and the transformer can handle only so many of those low voltage lamps. So the transformer wattage is what you would calculate in putting together your calculations. Now, the code says that you have to have individual space control for the lights. People have to be able to have access to a switch to turn them on and off. There has to be at least one for each room or space enclosed by ceiling height partitions, full height partitions. Every office has to have at least one control. Now, in large spaces, up to 10,000 square feet, each 2,500 square feet has to have a control. In spaces greater than 10,000 square feet, each 10,000 square feet has to have one control. Now, obviously, you may have a lot of lights in that space in large areas, and one switch may not be able to handle the current for all those lights. That switch would switch a relay, and the relay would be a heavy-duty one with the contacts rated to carry the hundreds of amperes that might be drawn. But nevertheless, it still says that you have to have these switches. Have to be readily accessible to the occupants. But if they're in a secured area where you might have vandalism considerations, they do say they can be located in a remote location. Hotels and motels have to have a switch by the entrance door that turns off all the lights in the room. Now, currently, that includes the bathroom. In the 2010 code, it's been modified to exempt the bathroom, so that if the bathroom door is closed and somebody may forget to check, they may turn off the lights, there may be somebody in the bathroom, everything goes dark, they can't find their way out. Unfamiliar space. Right now, the code says that the bathroom lights have to be on that switch. Now, it doesn't say what kind of switch. It can be a toggle switch, but quite frequently you'll find an electronic switch. All the motels and hotels are now using these electronic key cards, little credit cards, magnetic stripes on them. So you take your room card, you unlock your room, you go in, and inside is this little receptacle. You put your key card in that receptacle, and it energizes the lights in the room. You can then go to the switches and turn them on and off as you wish. But as you leave, you take your key card with you, and that automatically shuts all the lights off in the room for energy-saving reasons. It leaves the heating and air conditioning system untouched, and it leaves the receptacles untouched. But all the permanently installed fixtures in the room are that way. Occupancy sensors, in other words, some kind of an electronic device to automatically sense when people are in the room, are required in classrooms, except K through 12. Elementary schools, high schools are accepted, and shop or laboratories. They're required in conference rooms and meeting rooms. They're required in employee and lunch break rooms. Additional controls are required for display lighting and accent lighting, all kinds of display lighting and retail situations are required to have separate controls. Non-visual lighting, what would non-visual lighting be? Think a heat lamp, maybe over a food serving line in a cafeteria. And demonstration lighting. Automatic lighting shut-off devices. You got to be able to shut these off automatically in any buildings larger than 5,000 square feet. It doesn't say spaces, it says buildings. So a small building, 5,000 square feet, has to have an automatic lighting shut-off control device. It can also be overridden by a local switch, but the override can't last longer than 4 hours. If somebody's working in there all night long, every 4 hours they're going to have to go over there and cycle that switch. There are some exceptions. Lighting that's required for 24-hour operation, patient care spaces in hospitals, or safety or security concerns. And here's how you can comply with the automatic shutoff. You're going to have a time of day controller, which is a time clock. It can control up to 25,000 square feet, not more than one floor. An occupant sensor can be used, or a signal from another control or alarm which indicates the area is unoccupied. Occupant sensors are being installed in classrooms, but in the wintertime, students come in and sit with their coats on. And an empty classroom is fair game for a study hall. So students may go into an empty classroom and sit there in the wintertime with their coats on, reading, motionless for long periods of time. So the occupant sensor has to be something that can detect not only heat, but motion or other means to determine if there's people in that room. You've got to be a multiple effect sensor. Application of automatic shutoff. Its intent is to apply to business entities or structures where the whole building control is practical. In other words, a store in a strip mall. We want to turn off outdoor lights in the daytime. We could do that by means of either photocells or by what's called an astronomical time clock. An astronomical time clock has a dial on it that is calibrated to the latitude at which it's installed. And you order that from the manufacturer when you buy the clock. And it varies the time of day according to the season. So it shuts the lights off at the appropriate dusk and dawn hours all during the year. A photo switch may not be appropriate in areas that have high ambient lighting. There may be areas nearby that have display lighting, maybe an automobile car lot, lit up brilliantly, which is allowed by the code. And you're next to that. Your photo cell may be fooled by the ambient lighting and the lighting next door. So that might be a time when you would install an astronomical time clock. Have to have a battery backup in case of power failure, so the time clocks keep their settings. And there are some exceptions. Exits from buildings or parking structures, covered vehicle entrances, or where required for safety or security or eye adaptation. The display lighting and retail applications, task lighting, non-visual, all these things are covered in these different paragraphs and how you control them. Now here's a situation that does not occur very much anymore because of electronic ballast, but it has to do with fluorescent fixtures that have 3 lamps in them. Typically, a ballast can control only 1 lamp or 2 lamps. There are no 3-lamp ballasts, at least the old-style magnetics. So they came up with a scheme called tandem wiring, where they would have 2 fixtures close together, it says closer than 10 feet, where they would have a 2-lamp ballast control 2 lamps in one fixture, 2-lamp ballast control 2 lamps in the other fixture, and a 2-lamp ballast in this fixture controlling 1 lamp here, in this fixture, and 1 in there. This is allowed, and this is recommended. But again, I think we're kind of getting away from this because the electronic ballasts don't waste energy. So we don't have to worry about having a 1-lamp ballast. There's some exceptions, of course. Fixtures that are more than 10 feet apart, pendant luminaires, luminaires with 3-lamp ballasts, if they're possible, emergency lighting with no available pair, or with 1-lamp high-frequency electronic ballast. And again, these are becoming more and more common. They're almost industry standard. So it's kind of doing away with this tandem wiring provision. Exit signs, they're limited to 5 watts per face, but that's easily done. We've been installing exit signs with LED lights for at least a generation that I know of, so they're very common. Exterior lighting power, there are power limitations for exterior lighting. How many watts can you use to light a space? Now, the levels of illumination are not covered in the code. They are covered by a group called the Illuminating Engineering Society in their recommendations. It's another technical group of lighting engineers who have researched the human performance of various tasks and situations, and they've determined in the range of visual acuity that's normal in the human race what the recommended lighting levels are. And there's a range of light levels. So the codes are telling us that we have to design to these lighting levels, but the energy code limits the amount of power that we can use in reaching those lighting levels. And that's called lighting power limitation. Some of these may be traded in the code. Some cannot be traded. And the efficacy comes into effect. The term efficacy is used in the energy code, and it's kind of an unusual term, but what it means is efficiency. And efficiency varies with the wattage of the lamp. The larger the lamp, the more efficient it is. And the style of the lamp. An incandescent lamp is very inefficient. The smaller incandescent lamps can put out only 9 lumens per watt. I have some at home. The larger incandescent lamps can go up to 19 lumens per watt. This is the efficiency or the efficacy of an incandescent lamp. Fluorescent lamps in the smaller sizes may be 30 lumens per watt, 20 lumens per watt in the small, tiny nightlight styles, or they can go up to approximately 60 lumens, and here's an example of 66 lumens per watt in the 40-watt fluorescent. Now, the different style fixtures have different efficiencies, different efficacies. And as you can see, the wattage, here's system wattage, small wattage lamps, system efficacy, incandescence range, always below 20 lumens per watt, down to as low as 9 lumens per watt in this range. And we're trying to get away from them. And federal legislation is now eliminating incandescent lamps. In 2012, the 150 and 200 watt incandescent lamps will be going away. 2013, the 100 watt lamps will be going away. 2014, the 40s and the 60s. There will be incandescent lamps left for special application. Remember the heat lamps I told you over food serving cafeteria lines. Oven lights. In ovens, they operate at high temperatures. There's nothing else that can withstand those high temperatures but a high temperature incandescent light. Refrigerator lights, they're on so seldom. They're on only when you open the refrigerator. They have to come on full brightness. There's no warm-up time that's allowed. And they go off as soon as you close the refrigerator. So those are exemptions. But basically all the rest of the incandescent lights will be going away and being slowly replaced by fluorescents or LEDs. Now, look at the efficiency or the efficacy of the fluorescent lights. And you can see in the range up to 300 watts, we're looking at efficacies anywhere between a little over 50 lumens per watt up to about 90 lumens per watt. Metal halide in the high pressure sodium fixtures are used in large area lighting. Metal halide can be used typically in a gymnasium indoors. They're a gas discharge lamp. The high pressure sodium give a yellow appearance light, so they're used outdoors. The low pressure sodium lamps, which are the most efficient of all, the color rendition is so poor that nobody uses them anymore. Everything looks brown. Every color looks brown outdoors under a low pressure sodium light, although they are the most efficient ones. So they're kind of not used anymore. But nevertheless, the metal halides you can see are up in the efficacy of over 100 lumens per watt, up to maybe 110, and the high pressure sodiums start out here about 95 and go up to 140 lumens per watt in the large fixtures. These fixtures in the 1,000 watt range would be those used on highways, interchanges, interstate highways, when you've got the very tall towers and maybe 6 lamps up there. The smaller systems, 400 watts, 250, these would be installed in commercial buildings, in parking lot lighting and sidewalk lighting. So basically they're telling us to use these higher efficacy lamps. So the exterior building lighting power allowance is specified, and there's tables, and there's areas, and there's particular usages outdoors where the power allowance is given. There are tradable surfaces. All these different things are exempt. Athletic playing fields, theatrical purposes, integral lighting, advertising signage or directional signage, temporary lighting, theme elements in amusement parks, public monuments, registered historic landmark, outdoor lighting is exempt. Here are lighting power density allowances for all different types of outdoor things. 0.15 watts per square foot. Again, it's a power allowance. And if we were going to use an 80 lumens per watt high pressure sodium fixture outside, we would have an average of 12 foot candles. Well, that's not uniform distribution. With a single source lamp, the light is distributed mostly underneath it. And they try to shape the reflectors to push the light outwards. And they give you some diagrams of how the light displays on the ground. And you reach a minimum lighting level. And for typical use in a parking lot, it's half a foot candle. And that's the light of a full moon at night. And so it may be 20 foot candles directly under the fixture, and then out to half a foot candle, at which point you will install another fixture and pick up at half a foot candle, and the lighting level will go up to 20 foot candles directly under the fixture, and then down to half a foot candle. And so you would install these lights. Well, the average would be 12 foot candles. Again, walkways, 1 watt per linear foot. Walkways, 10 feet wide or greater, 0.2 of a watt per square foot, which equates to 16 foot candles with that same fixture. Stairways, 1 watt per square foot. Here's tradable surfaces and non-tradable. Building facades, automatic teller machines, entrances, gatehouse inspection stations, all these things are covered, and there's lots of exceptions. The lighting power allowance exceptions, refrigerator display cases, retail display windows, all these different things are exempt. Here are some examples how the code describes the locations of these various areas. We can have outdoor parking area, we can have a sidewalk outside, we can have an entrance, we have a display window that displays to the outside, we can have display lighting in a store, we can have corridor lighting. And we can use a couple of different methods of calculating. We can use the building area method. If you have a building with a floor that has almost the same type of spaces all over the entire floor, we can use the building area method and go on a square foot basis for the whole floor. However, if you have mixed use, offices, classrooms, laboratories, toilets, all sorts of different things on the same floor, then you'd use a space by space. The gross lighted area is measured from the exterior face of the exterior wall. It includes the thickness of all interior partitions. It includes elevator shafts, piping chases, duct chases. It's a very generous method, and I would like to use that to the extent possible. It's a very simple method of using it. And here are building area allowances. And here is the previous code, the 1999 ASHRAE code. And as you can see, the power density allowance has gone from 1.4 to 1.2 watts per square foot for a courthouse. For an office, it's 1.3 down to 1 watt per square foot. So all these things have generally dropped, although some things have gone up a little bit. The space by space method is used when you cannot use the building area method. And you have to do a lot more calculations, and it's the interior spaces themselves. We don't have partitions and chases and anything that can't be occupied by humans. In the space-by-space lighting power density method, courthouses actually in the old code were allowed 1.5. They've gone up to 1.9. We're allowing more lighting now inside of courthouses. Bars are down. Cafeteria fast food is up, as is family dining. Dormitories are down. Exercise centers down. And enclosed offices are down from 1.5 watts per square foot to 1.1. The 2010 code, which has been written and reviewed and published, nobody's adopted it yet, no states are using it, but the 2010 code drops these an additional 30% on average. So the 2010 code is going to become so restrictive that it's going to try to encourage the use of task lighting. Now, we haven't adopted the 2010 code yet. And I don't know if the state will or when it will. But we're going to be looking at a whole different means of doing business with lighting in spaces. Additional lighting power is allowed. There's a whole bunch of different categories in retail spaces and the type of retail space. There are categories, areas 1, 2, 3, and 4, and how many watts per square foot you can actually put. And you're talking about a small area within a store, would not be partitioned off, but it's next to this type of display, or next to a clothing display, or next to a jewelry display, or next to an electronics display. All of those things are covered. There are no submittals associated with the lighting requirements, believe it or not. Other equipment, such as motors, have to have a minimum efficiency as specified in the Energy Policy Act of 1992. And there are different frame motors. There are U-frame motors, there are T-frame motors, and this is all part of the National Electrical Manufacturers Association categories. And different motors have different efficiencies. Less heat is wasted. And basically what they're saying is that motors must now comply with the new higher efficiency standards. The energy cost budget method allows you to trade off different areas and different systems amongst one another. It's a computer calculation that is the most flexible method of complying with the code. In fact, many engineers will do this automatically because I myself as a design engineer start every project by doing a heating and cooling load calculation. And at the same time, we can put in all the values of lighting, watts per square foot. And we can then run the program and see if it meets the energy code. And if it doesn't, we can begin to trade one thing against another. And this is allowed. And this is a method of dealing with unique designs that cannot be permitted under the prescriptive method. And this is the basis of the lead calculation method in Appendix G. That is the non-code required method of saying that you are this much more efficient than the energy codes. You have designed an intelligent building that uses very little energy. That's the LEED standards. The energy cost budget method, you have to have an approved building envelope design prior to submitting this. So it's got to be done kind of after the fact. You have to meet all of the basic mandatory requirements. You have to meet the energy efficiency level of all the components, the heating and air conditioning, the electrical stuff. And you must document this in great detail. The details are specified right here in 11.1.5. This chapter 11 is all about the energy cost budget method. You have to use an approved simulation program. Use the climate data for your location, current data. You have to put in the energy rates that are current at the local location, and you have to document that from something, an energy bill or some kind of a statement from the local utility. You have to use the same simulation program, all the data, the climate data, the utility rates for both the example building and the basic building when you compare the two. You have to develop your proposed building design, choose your budget building HVAC system. If you're looking at a LEED system, you're using a whole number of different components, a number of different restrictions and limitations. Again, Appendix G has got a whole bunch more stuff in addition to Chapter 11. And there's some references in Section 12, and they're called normative. And these references, which are code books, standards, publications of other entities, are required. They are part of the energy code and they are required. So even though they're just a reference, you might get caught by something which is tucked away in the pages of one of these normative references. Appendix A, again, is all the pre-calculated U values for all the different building envelopes. Appendix B talks about a tabulated county-by-county list of all the counties in the United States for the climate data. Appendix C is the trade-off option, the computer simulation. Appendix D, again, it's a normative, it's a required appendix, is all the climactic data. And Appendix E are other references. F is description of addenda, information on addenda in the ASHRAE code. Again, the addenda has not been adopted by the state of Michigan, so that's not part of our requirements. 44 addenda were issued before the code was updated to the 2010. But all those 44 addenda are not part of our code. And it's instructions in Appendix G for using the code in relation to certifying a LEED rated building. This concludes our presentation of the Michigan Commercial